Curvature. Recall from the previous lesson that a curve C is smooth on an interval if C can be parametrized with a vector-valued function R of t, whose derivative is continuous and non-zero on the interval. We may say that such a vector-valued function R of t is a smooth vector-valued function or a smooth parametrization of the curve C. Essentially, a smooth curve has no sharp edges or cusps. When the tangent vector to a smooth curve turns, it does so continuously. If C is a smooth curve parametrized with a smooth vector-valued function R of S, where S is an arc length parameter, then the curvature of C is written as kappa of S. That's the Greek letter kappa that we use for curvature. It's the length of the derivative of the unit tangent vector with respect to S, which is also equal to the length of R double prime of S. Let's check that those two things are equal. To see this, first recall from the last lesson that the length of R prime of S, which we could also write as the length of dr ds, is 1. So the unit tangent vector at S is R prime of S over the length of R prime of S, which is just R prime of S because the denominator there is 1. Therefore, the derivative of the unit tangent vector with respect to S is R double prime of S, and taking the length of each side of that equation, we get our result. Let's look at a picture of a typical curve C parametrized by R of S, just to understand geometrically what curvature means. Toward the bottom of the curve here, we would say that the curvature is relatively small because the curve is somewhat linear there. It's not curving too much. Whereas toward the top of the curve here, we have a larger curvature because we are curving quite a bit more than at the bottom of the curve. As an example, let's show that the curvature of a line is 0. As always, you should pause the video, try to show this yourself first, and then resume the video to see how I do it. Okay, let's start with an arc length parametrization of a line. R of S equals R sub 0 plus U times S. This is the line passing through the point R0 and parallel to the unit vector U. Note that in order for this to be an arc length parametrization, remember that the vector that we use has to be a unit vector. Now, R prime of S is just U because the derivative of R0 is 0 and the derivative of the constant vector times S is just that constant vector. So R double prime of S is the derivative of a constant vector, which is just the 0 vector. Therefore, the curvature at S is the length of R double prime of S, or the length of the 0 vector, which is just 0. This is what we wanted to show. Now, in practice, it would be a bit tedious to have to reparametrize every curve in terms of arc length before computing the curvature. Luckily, there's a nice theorem here that allows us to compute the curvature of an arbitrary parametrization. There are two formulas here we could use for an arbitrary parametrization. The curvature at t is the length of the derivative of the unit tangent vector at t divided by the length of R prime of t. And that in turn is equal to the length of the cross product of the derivative of R of t and the second derivative of R of t divided by the length of R prime of t cubed. In practice, I will usually use the second formula there involving the cross product. As another theorem, if we happen to have a scalar function, y equal to f of x, then the curvature at x is the absolute value of f double prime of x over 1 plus the square of f prime of x, all to the 3 halves. So that I don't get distracted with the proofs of these theorems, I'm going to move on to some examples next. But for those of you that are interested, I will provide proofs of these theorems at the end of this lesson. Let's try an example. Again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Find the curvature of the function f of x equals x cubed at the origin. Since this is a scalar function, I'm going to use the appropriate curvature formula, which I'll put up in the right-hand corner here. So we're going to need f prime of x, which is 3x squared, and f double prime of x, which is 6x. Plugging that into the curvature formula, we have the absolute value of 6x over 1 plus 3x squared to the 3 halves, which we could simplify to the absolute value of 6x over 1 plus 9x to the 4th, all to the 3 halves. Since we want the curvature at the origin, we're going to plug in a 0 for x, and we get 0 over 1 plus 0 to the 3 halves, or just 0 over 1, or just 0. So we see that the desired curvature is 0. Let's try an example involving a vector-valued function. Again, pause the video, try this yourself, and then resume the video. Find the curvature of the circular helix r of t equals 2 cosine ti plus 2 sine tj plus 3tk. This time we're going to use the second curvature formula for vector-valued functions. Let's start by computing r prime of t cross r double prime of t. So inside our determinant, we're going to put for the second row the derivatives of each component there. The derivative of 2 cosine t is negative 2 sine t. The derivative of 2 sine t is 2 cosine t. And the derivative of 3t is 3. For the third row, we take the derivative of the derivative. So the derivative of negative 2 sine t is negative 2 cosine t. The derivative of 2 cosine t is negative 2 sine t. And the derivative of 3 is 0. Okay, so let's evaluate this. The I component is 0 plus 6 sine t. For the j component, we get negative 6 cosine t minus 0. And for the k component, we have 4 sine squared t plus 4 cosine squared t. We could factor out the 4 and use the Pythagorean identity to get 4 times 1, which is 4. So we get 4k. Now the length of that is going to be the square root of 36 sine squared t plus 36 cosine squared t plus 16. We could factor out the 36 and replace, once again, sine squared t plus cosine squared t by 1 to get 36 plus 16, which is 52 under that square root. 52 can be factored as 4 times 13. Splitting up the square root, we get 2 root 13. I just want to mention that this little trick involving factoring out a constant from sine squared t plus cosine squared t and then using the Pythagorean identity to replace that with 1 is going to occur very often throughout these lessons. So try to understand how to do that so you could do it quickly and save a lot of time. Okay, now I'm going to go ahead and plug what we have into the formula for curvature. Up top, we already found that the length of the cross product is 2 root 13. And let me do the bottom here, the length of r prime of t. Now, to see r prime of t, just look at the purple row in that determinant there. And we're going to apply the same trick that we did a couple of times already. We have 4 sine squared t plus 4 cosine squared t, which after factoring and using the Pythagorean identity is just 4, plus 9. And that's what goes under the square root there. So we wind up with 2 root 13 over root 13 cubed. We could write root 13 cubed as 13 root 13. And reducing that fraction, we get 2 over 13. Notice that in this case, The curvature came out to be a constant. That's because we have a circular helix, so that at each point on this curve, the curvature is the same. That won't always be true. In general, the curvature will be a function of t. Let's look at an example that's a little more complicated. Find the curvature of the ellipse r of t equals 2 cosine ti plus 3 sine tj for t between 0 and 2 pi at the endpoints of the major and minor axes. We're going to use the same curvature formula as in the last example. And let's start by computing the cross product of the derivative and second derivative. So the first derivative, we get the derivative of 2 cosine t is negative 2 sine t, and the derivative of 3 sine t is 3 cosine t. Since there's no k component, we just get 0 there. And now differentiate again. The derivative of negative 2 sine t is negative 2 cosine t. The derivative of 3 cosine t is negative 3 sine t. And once again, we have 0 there. The I and j components both come out to 0. And for the k component, we get 6 sine squared t plus 6 cosine squared t, which by the usual methods that we've seen several times already is just 6. So the cross product here is 6k. So now let's compute the curvature. So on top, the length of 6k is just 6. And on the bottom, we get the square root of 4 sine squared t plus 9 cosine squared t. To compute that, we use the middle row or the purple row of that determinant there. Notice that in this case, the curvature is not constant. It depends on t. Let's look at a graph of our ellipse. Notice that to sketch the graph of this ellipse, we move 2 units left and right along the minor axis to get those 2 vertices because of the 2 in front of the cosine t, and 3 units up and down from the origin to get the vertices on the major axis because of the 3 in front of the sine t. So the endpoints of the minor axis occur when t is equal to 0 and t is equal to pi. So first we want to compute kappa of 0 and kappa of pi corresponding to the points 2, 0 and negative 2, 0. And both of those values are going to come out the same. We get 6 over the square root of 9 cubed because the sine of 0 and the sine of pi are both 0. And the cosine of 0 is 1. The cosine of pi is negative 1, but we're squaring it. So both times we get 9 times 1, which is just 9 under that square root. The square root of 9 is just 3, and 3 cubed is 27. 6 over 27 reduces to 2/9. Let's now look at what we get when t is pi over 2 and t is 3 pi over 2. These correspond to the points 0, 3 and 0, negative 3, the 2 endpoints of the major axis. This time, we get 6 over the square root of 4 cubed because the cosine of these values is 0 and the sine of these values is plus or minus 1, but we're squaring, so we always just get 4 times 1, which is 4. So the square root of 4 is 2, cubing that we get 8. 6 over 8 reduces to 3/4. As promised, I'm now going to prove these 2 theorems. Let's start with the first result in the first theorem, that kappa of t is the length of the derivative of the unit tangent vector divided by the derivative of r of t. By the chain rule, we have that the derivative of the unit tangent vector with respect to t is the derivative of the unit tangent vector with respect to s times ds dt. So kappa, which is defined as the length of the derivative of the unit tangent vector with respect to s, dividing that first equation we have there by ds dt, we see that we have this, and we can replace ds dt by the length of r prime of t. We saw that that was true in the previous lesson. And the derivative of the unit tangent with respect to t can be written as t prime of t. So we have our first result. Now let's prove that this is also equal to the length of the cross product of the derivative and second derivative over the length of r prime of t cubed. So first, note that by definition, t of t is r prime of t over the length of r prime of t. And we saw in the previous lesson that ds dt is the length of r prime of t. From the first equation, we get that r prime of t is the length of r prime of t times t of t. And from the second equation, we can replace the length of r prime of t by ds dt. Now, differentiating both sides of that last equation we have r double prime of t is by the product rule, ds dt times t prime of t, plus the second derivative of s with respect to t times t of t. Now we take the cross product. Using the fact that the cross product is distributive over addition, we get ds dt t of t cross ds dt t prime of t plus ds dt t of t cross the second derivative of s with respect to t times t of t. Now, the second term there is just 0 because the two factors in the cross product are scalar multiples of each other. And when you take the cross product of parallel vectors, you always get 0. We could pull out the scalars, ds dt. So we have ds dt squared times t of t cross t prime of t. Taking the length, we get ds dt squared times the length of t cross t prime of t. Usually we would take the absolute value of the scalar, but since it's squared, we already know it's non-negative. Now, using the main theorem on lengths of cross products, we can write that length of the cross product as the length of t times the length of t prime of t times the sine of pi over 2. The angle there is pi over 2 because t of t is orthogonal to t prime of t. Now, the length of t is 1, and the sine of pi over 2 is 1, so we get ds dt squared times the length of t prime of t. Solving for the length of t prime of t, we get the length of that cross product divided by ds dt squared. And remember from the beginning of the proof here that ds dt can be replaced by the length of r prime of t. And finally, kappa of t is the length of t prime of t, which we just expressed in terms of r, divided by the length of r prime of t. So we get one more factor of the length of r prime of t in the denominator, giving us our result. Now, finally, for the last theorem on computing the curvature for a scalar function, we start by parametrizing y equals f of x as r of t equals ti plus f of tj. In other words, we just set x equal to t, and then it follows that y equals f of x is f of t. Okay, so we have r prime of t is we differentiate component by component to get I plus f prime of tj. And r double prime of t, the derivative of I is just 0, and the derivative of f prime of tj is f double prime of tj. We now take the cross product. Using the fact that the cross product is distributive over addition, we get I cross f double prime of tj plus f prime of tj cross f double prime of tj. For the first term there, we could pull out the scalar f double prime of t and then use the fact that I cross j is k. For the second term there, we're taking the cross product of two things that are scalar multiples of each other, so we just get 0. So we wind up with f double prime of t k. So now the curvature is the length of the cross product that we just found divided by the length of r prime of t cubed. So the length of f double prime of t k over the length of I plus f prime of t j cubed. So up top, we get the absolute value of f double prime of t, and on the bottom, we get the square root of 1 plus f prime of t squared, all cubed, which we could rewrite as to the 3/2 power. And also, since we set x equal to t in the beginning, we could replace the t's by x's at the end here.